Muy buenas tardes a todos, bienvenidos a otra realización del Seminario de Ingeniería Industrial y el Major en Investigación Operativa. Hoy día tenemos el placer y el honor de contar con la profesora Merve Bodur, que es profesora asociada de la Escuela de Matemáticas en la Universidad de Edimburgo. Merve and I will turn to English. Merve is an associate professor in the School of Mathematics at the University of Edinburgh. She obtained her PhD from University of Wisconsin-Madison and did a postdoc at Georgia Tech. She received her Bachelor in Science and Industrial Engineering and Mathematics from Boğaziçi University in Turkey. Her main research areas are optimization under uncertainty, and most notably for discrete optimization problems with applications in a variety of areas such as scheduling, transportation, healthcare, telecommunications, and power systems. And today she's going to present her research, Neural Approximate Dynamic Programming for the Ultra-Fast Order Dispatching Problem. Thank you, Professor Bodur. You have 40 minutes to present. Thank you.
Okay, thank you so very much for the introduction, Andrew. You said 40, so maybe I will something like 35.
I mean, if it's longer, that's okay.
Yeah, we'll see how it goes, how you feel, and accordingly we will adjust. So I prepared more than what my time might permit, so we can skip or we can cover the whole thing based on your interest. So first of all, I would like to thank everyone here in the room, especially the front row, for the hospitality. I do enjoy every single time I visit, so it's such a pleasure, wonderful people, but especially also I would like to thank my wonderful host, Margarita Castro. So yeah, I am coming from the UK. I used to be in Canada before, and now I recently moved to UK, School of Mathematics in Edinburgh. So this is a joint group with my collaborators from Toronto, my collaborator Vijay Çelik, and our co-supervised student Arash from Toronto Metropolitan University. So I would like to tell you a little bit about this ultra-fast order dispatching problem, and specifically this new methodology that we got to learn and really enjoyed and really tried to understand its advantages, and we found a nice application for it. So I also hope to inspire some of you for this recent methodological idea that we didn't develop. We borrowed from literature, but it requires a lot of tailoring towards your problem. So I will hope to a little teach you guys if you haven't seen Approximate Dynamic Programming to start with, and also it is neural network incorporated version Neural Approximate Dynamic Programming. So where's our motivation coming from? So this is actually one of my collaborators, Vijay Çelik, the professor in the Toronto Metropolitan University. He actually collaborated with this Turkish company called Getir. So Getir means bring in Turkish. So this is a Turkish company who started their operations in the most hectic city in Turkey, Istanbul, millions and millions of people in a very compact, small area. So it is very crowded. But the important mission of the company, the reason that they built the company, is this ultra-fast delivery. And I will shortly explain what they hope to achieve by this ultra-fast aspect of the delivery. And later on, actually, this company grew pretty fast. They expanded in Europe a little bit. And of course, after the pandemic, unfortunately, they had to withdraw from some companies. But also there was a similar company hoping to do ultra-fast deliveries in Germany called Gorillas. This was also a very successful one, which is in turn later on acquired by Getir as well. But the company grew. Now they have almost like 20 million customers, more than 30,000 couriers to do the deliveries. And it was worth of $12 billion in the past couple of years. So what the example you can think of, what type of deliveries? They have many business models. They deliver different things, but the most important example, like I would say, is the grocery deliveries. So, and then because you are there operating in this very crowded city, and their mission is ultra fast. And what do I mean by ultra fast? Their mission, fundamental goal, is to make the deliveries in a matter of minutes, if possible, 10 minutes. That's how they started. So when you basically go online, you give your grocery store order, then as soon as this order is accepted by your system, they hope to drop your order at your doorstep in a matter of 10 minutes. Of course, this may not be feasible, but that's what they are hoping to achieve. So they have some other services like water or a bunch of other things, even meal deliveries. They also collaborate with restaurants, whatnot. But we can think of, for my application in mind, we can think of groceries as the important thing to be delivered. And the goal is, let's say, the target is 10 minutes or so, or some other very strict deadline that you hope to achieve. And I will note this, but this strict, very strict deadline, actually it will justify that they would like to operate from a single warehouse operating in a specific, like relatively small region, right? You don't need to consider multiple warehouses that needs to coordinate in the set. And then of course they would like to meet as many orders as possible, but there's a trade-off. If you would like to maximize the deliveries that you are making, there is also the trade-off between how fast you can deliver these orders. So because this is such a strict setting that you are operating on, for the sake of efficiency, maximizing the efficiency, optimization will be very, very important. But this is just one example. This is how we got started, inspired by this Getter's ultra-fast delivery setting. I will also stick into ultra-fast delivery, but the generalization of this problem you can think of, and you can even think of extending the ideas that I will show shortly to this generalized version of the problem, namely the same-day delivery problem. And after online shopping became so huge, and especially after the effect of the pandemic, all this growth, it led to more and more careful investigation of the same-day delivery problem. And especially all the major players like Amazon, Target, Walmart, they actually expanded their services, most notably after the pandemic, to do the same-day deliveries. Okay, and inspired by this remarkable growth of the same delivery demand, the official problem is introduced to the academic literature in 2019 as the same-day delivery problem. So what we are trying to do is, because even if it's 10 minutes as in Getter's mission case, or it is more like Amazon case, whatnot, same-day delivery, you are nevertheless working with these very tight deadlines, right? And because you would like to basically deliver everything fast in this strict timeline setting, it justifies the single warehouse that you need to operate for optimization's sake. So for every warehouse, you can think of, they have some sort of a geographical region they are gonna serve into, and you can only do optimization per warehouse. So that's why we will be looking into a single centralized warehouse with a predetermined operational region. And orders, they will, of course, in reality, there is uncertainty, it's inevitable. Orders will be arriving in a stochastic manner, in a dynamic stochastic manner. And we all have a bunch of couriers available in our fleet who's going to be doing the deliveries as the orders come. So in terms of the main decision aspects of the problem, you can think of many, but the most notable ones would be, as the orders come in, you need to decide whether you are going to accept or reject them. And accordingly, for those that are accepted, you need to match them with their available or soon to be available couriers. And then you also need to decide how you are going to dispatch the couriers to make the deliveries, and during which you also need to do the routes of your couriers, right? There are a lot of important aspects. And one thing that is very, very important for what we are studying is the strict time constraints that you need to abide by. And your main goal will be maximizing the orders served in your operational horizon. And this is the version of the SDD problem introduced to the literature in 2019. And if you look at this problem, there are so many challenges, but the most important ones will be, there are various aspects, as in the matching, dispatching, routing aspects, among the others that I will also slowly reveal. And you need to make real-time decision making, because we would like to deliver everything fast in a matter of minutes or hours, or at least in the same day, and they come dynamically in a stochastic fashion. As orders come during the day, you have to make decisions in real time. You cannot say, okay, I accept your order, let me see in the next couple of days how I'm gonna dispatch your order, right? So no, you have to make the decisions in real time, which requires a methodology that is suitable to quickly give you near optimal solutions. And of course, uncertainty is another challenging factor. We don't know the timing of the orders and the volume of the orders and their possible destinations. Okay, so if you look at the same-day delivery literature, there are a fair amount of works, I would say, and there have been different strategies that we see here, from machine learning models to more optimization approaches like heuristics, combinatorial optimization approaches. There's a very good literature. And in fact, if you look at them, we can categorize them into two. So same-day delivery, it has two sub-problems, main sub-problems. One is the vehicle routing aspect of it for the routing of the couriers, and the other one is this dispatching. Either it could be amounting to when you would like to dispatch certain couriers, or basically which orders to assign to the couriers, whatnot. So we can categorize the literature in two. Basically, the routing ones, the ones focusing on the routing aspect, and the green ones here, the ones focusing on the dispatching aspect, which we will belong to. And here, one specific one I would like to especially point out is Matthias actually has a paper from 2017 on this order dispatching problem for same-day delivery. Because he's here, I'm not gonna mention the drawbacks of this. But as you can see from the table, what we hope to do is we have these different characteristics, whether your couriers can have more than one capacity, especially heterogeneous couriers you can accommodate, whether you have multiple vehicles in the system, whether you are working with these strict delivery time deadlines, whether you can bundle the orders to further improve the efficiency of the delivery system, as well as whether you explicitly account for the courier's shifts. So if you look at these aspects, then we would like to incorporate all of them into our mathematical models and solution methods accordingly. And it hasn't been studied as is, all the aspects being there in the literature to the best of our knowledge. And as I said, we are belonging into the dispatching aspect of this problem. We will look into that. And methodology-wise, I will hope to introduce you this new thing that I find pretty cool, NeurADP. Okay, and in the literature, the most closely related one to our work is this Kavuk et al. Paper from a couple of years ago, because these guys actually, they collaborated with this Turkish company Getir, and they indeed studied Getir's setting. But they have significant disadvantages based on simplifications that they have made in their model. So I will show you exactly how we extended their version to come up with some much better representation of the realistic operational setting. And of course, our methodology will be different than theirs as well. But the key aspect that we need to carefully play with is this urgent delivery requirement for the sake of ultra-fast deliveries. So this brings these critical time constraints to about model, and again we have to make real-time decisions. That is important, especially considering the stochastic demands. Your policies should be able to adapt really easily to varying demand patterns over time. And because of this, again, ultra-fast delivery setting, we don't have to worry about so much about the routing aspect. Actually, what it becomes is we don't need to worry about like time to dispatch the couriers, because there's this urgency. It doesn't become an important decision anymore. So the problem actually technically more so reduces to this courier resource allocation problem. So you have these couriers as your resources, and there's demand how you use your resources in the best way possible. So it's going to become just more so an assignment problem. So we don't have to worry about these aspects that is mostly studied in literature as dispatch times or transportation mode decisions. Okay. So, as I said, the closest work to ours is only paper from the literature is this 2022 paper of Kavuk et al. So what they did is they exactly looked at this Getir's ultra-fast delivery setting, but on top of their setting now, we are introducing some important key aspects to this problem definition. One, we are introducing order batching possibilities. So now we can actually batch the orders and assign couriers batches of orders. Second one, we are introducing these courier queues. So if a courier is already over there going and making some deliveries, we are gonna in the depot keep a queue for them, and that will help also improving the efficiency of this operational system. And we also are gonna do, compared to theirs, we are gonna do actually solve the matching problem. So they have a heuristic already predefined some rules that are making the assignment. So we are gonna do the full optimization. And in their work, all the Getir wants to do this 10 minutes. They do not impose this hard deadline restriction. Instead, they have flexible delivery times. There's no strict hard deadlines. They just penalize the delays. So in their version, for instance, some order might be delivered in a matter of 45 minutes. Then if your target was 10, they're just gonna penalize the 35 minutes of delay. But for us, we are gonna have the hard deadlines. If you are not gonna be able to fulfill the deadline of the customer, you don't accept it in the first place. Let them order another time. So whenever you accept an order, you ensure that you are gonna be satisfying these hard time deadlines. And also we expand their problem size, especially we wanted to look at some different, we created some novel test instances actually to look at some other geographical regions, maybe larger areas, to do some more sensitivity analysis to understand how the operations will be impacted for certain parameters. And also, of course, we are going to do sensitivity analysis. From the methodology perspective now, we are going to adopt this NeurADP, approximate dynamic programming methodology, because it is actually proposed for right pooling problem. I will explain shortly, but it can actually handle very well one-to-many matching problems. So in the earlier work from the literature, they did only one-to-one, which simplifies the problem quite a bit. So I'm going to tell you hopefully, and it will be clear soon enough, why we chose, why it is amenable and expected to work well for our problem setting. And this NeurADP, it's been recently introduced to the literature for the specific right pooling framework, and this our work constitutes the very first use of it from its original context. And what we will do is we will then compare our NeurADP-based policies to some benchmark policies that are, I will say, non-trivial, especially myopic and deep RL-based policies. And in order to assess the quality of our solutions, we will also be getting some non-trivial upper bound. We will solve some optimization problems, whatnot, to see what best we can at least hope to do, get a better upper bound to see whether our solutions are close to that bound or not. Okay. At the high level, why we picked this methodology, NeurADP, I haven't told you what it is doing, but at least I can compare it with the alternatives from the commonly used alternatives. So, compared to myopic type of policies, what does myopic do? Myopic ignores the future, right? So you are given the state of your system, you will make your decisions now just based on that. You don't really care about the impact of your current decisions in your future decisions and the system performance. So compared to myopic, NeurADP framework, actually, it would very well be considering consequences of our decisions in our future. Compared to deep reinforcement learning based methodology, and especially this methodology has been employed in the Skouk et al. Paper, NeurADP can handle much more complex decisions. And in our setting, we will have actually, in this paper, they will only decide whether you should accept or reject an order that comes into your system. And for everything else, assignment to couriers, routing, they have preset rules, but we will optimize over everything. And finally, compared to traditional approximate dynamic programming, the advantage of neural network part, it will allow us to learn much more complex, large-scale problem settings efficiently. Okay, so what comes next? I will briefly introduce you our full problem definition and our MDP model in a general way, and I will tell a little bit about how the traditional ADP methodology works so that I can show you what we don't expect this to be successfully working for our setting, and that will motivate NeurADP, and hopefully I will explain the details of NeurADP. Okay, so our problem-specific setting. So we have a single warehouse, right, an operational setting, and the main goal will be, as the orders come to our system, how to match our couriers with the incoming online orders with the goal of maximizing the number of orders that are fulfilled, successfully delivered in our strict time limits. And as I said, the ultra-fast delivery setting justifies the single warehouse setting. For the operational horizon, we are looking at a whole day, which rolls over. So we are going to consider, for our optimization sake, a 24-hour operational horizon, which we will discretize into, say, 5-minute or even more granular intervals. Okay, so then how orders come into the system? First and foremost, there is uncertainty. They arrive to the system in a stochastic fashion. And the stochastic model, you need to use, of course, your historical data, but also incorporate some spatial and temporal patterns of the data. So orders come in a stochastic fashion to the system. And important thing is orders might come in batches. For instance, if our horizon is divided into these 5-minute intervals, in 5 minutes, there might be multiple orders joining to our or coming to our system. And each order will have a pre-specific destination and hard set delivery deadlines. So an order or a batch of orders, let's say these 2 orders came into our system, right? So if you decide to assign any order or maybe these 2 as a batch to a courier, then as soon as you accept the order to your system, you guarantee to this customer that if your target is 10 minutes, as you say, accept this order, you ensure that this customer will receive it in 10 minutes. So you guarantee the deadline. Otherwise, if you don't think you can meet that deadline, you reject the order and let them order at any time. Okay, with respect to the couriers, first of all, we are going to consider heterogeneous. So our couriers, they will differ in 2 main aspects. First, they will have their own individual shifts that they are working on during the day, and they might have their own vehicle, different capacities, if you like. Okay, in terms of now how we operate with the couriers, there are 2 kinds of couriers. One is already at the warehouse, idle, waiting for a task and assignment, and another one is currently busy, it's not available, it's doing some deliveries. So if you have a courier, this red card that is already available at your warehouse, then if these orders came into the system and you decided to assign both or one of them to this red car, it has to be dispatched right away. So that's because, again, we have this ultra fast thing. So as soon as you make an assignment to a courier that is available at the warehouse, you are going to dispatch it at the time period right away. On the other hand, if you have a busy courier like the blue card there, then we cannot assign any new orders for it to be delivered at the moment, but we are introducing this queue concept. So for the blue car, it's busy. It still needs to drop one order and then come back to warehouse. But we are keeping at the warehouse for this blue guy a queue. So we can also, from the coming orders, we can pick some or in batches and put to the queue of this guy. And the important thing is, when this blue car, as soon as it returns to the depot, we look at this queue. If there is any order collected in its queue, we are going to dispatch it right away. Okay. So as soon as like someone becomes available at the depot and there's an assignment for them, they are dispatched right away. And for the delivery guys, there's no option for preemptive depots. Whatever they are dispatched with, and we are going to tell them the route as well. They are going to go drop all of them and then come back to the depot. And before we dispatch them for a set with a set of orders, we are also going to give them the optimal route so that they can come back to the depot as soon as possible. Okay, so this is our problem setting. If any questions, please, by the way, I forgot to mention, feel free to interrupt me at any time.
Isn't there some time to pick to do the picking of the items you ordered, or is that ready to
For the
be,
couriers or customers?
Actually, I order a Coke.
Yes.
Is like doesn't someone have to go inside the warehouse to pick the?
Yeah, indeed, that's a great question. Especially let me give you the example specifically from the getter setting. So these are like they're operating with relatively small stores, right? We see a lot here in Santiago. So there are pickers in these stores. As soon as a call comes in and then it is accepted the system, there's an announcement. It goes into someone's assignment list. They have the list. They immediately pick and prepare them into these. Put them into these bags to be delivered for your customer. Maybe you ordered a Coke and something, right? You ordered maybe 3 things. The picker's goal in the store is to collect them and put them into the bag and leave them at the door ASAP. The pickers for each order, how large it is, they aim to collect everything in less than a minute.
Okay.
And in Getter's case specifically, if they actually collect them in less than 40 seconds or so, they get a bonus for each order. So everything is happening very fast, indeed.
Okay.
But there are pickers working in the warehouse.
Okay.
But because of our discretization, which is usually like minutes, we don't specifically count for seconds for that picking operation. But picking is happening already fast. Any other questions about our problem definition? Cool. So let me just introduce the modeling framework that we use. I'm not going to give you all the gritty details, but pretty much we are proposing for this dynamic optimization under uncertainty problem, a Markov decision process type of a model. And here are the main components of an MDP model. I will go quickly. Most of you might be familiar with it. So the main components of an MDP model, you have to have the state of the system at the time period T, we discretize, right? And at each time period T, you need to decide what to do, your action vector. And as you go from stage T to period T plus 1, some uncertainty will be observed, right? That will be the W of T plus 1. And then you need to make a transition. Given your current state, your actions to be made now, you decided on that, and the new uncertainty is observed. This function will make you the transition to the next state of the system. And the goal will be maximizing the expected reward because there is uncertainty. We need to put an expectation type of an operator to make it something deterministic to be optimized over. Okay, so now let's quickly review these components for our specific ultra-fast delivery, this order dispatching problem. So our state vector will have 2 subvectors. One will be for couriers in the system. The other one will be for the orders that are currently in the system at that time period. And for each of these things, you need to basically keep track of a lot of features and accordingly their values. So for couriers, for instance, you need to keep track of for all the couriers that are in your system right now, you need to keep track of their shift start time so that you will know when they will be actually going home. So you are not gonna make further assignments. When, if they are currently delivering an order, when they will be back to the depot, and their queue information. If they are busy, we will be keeping a set of orders in their queues to be picked up upon their return, so that the queue information we will be collecting. For the orders, as simple as we will be keeping record of their destination and their delivery deadline, which is determined based on when they join the system. What type of decisions we would like to make? Two main types of decisions we would like to make. When orders arrive, whether you accept this order or say, sorry, come back later. Or for the accepted orders now, let's say a batch of orders arrived, say 10 orders arrived in this 5 minutes, then you decided to accept 8 of them. So now for these 8 accepted, you need to decide which ones you can combine and assign to your couriers, either ones available in the warehouse or the ones that are busy. You can assign these batch of orders among the ones you accepted to their queues. So if you're an integer programming person, you know very well that, yes, there are so many like tedious decisions to be made, but we can build a mixed integer programming model for this, right? So I can actually, if this is my AT vector, I can build this mixed integer programming set to describe all of these constraints that I have in mind. For instance, I can write a MIP model where I would, first of all, I will be coming these order of batches in the system. The ones that I accepted, you will have a binary variable, whether you accept it or not. For the ones with the binary variable is equal to 1 that are accepted, you need to assign them to a courier, right? So you can create some variables to partition the accepted orders so that then each partition will be assigned to a courier or a courier queue. But the key one, and yeah, of course, you have to meet the capacities, whatnot, but the key, I think, the difficult part of this model will be for each courier in your system, you need to also ensure, because of the delivery deadlines, right? Each order has a deadline, and you need to ensure as soon as you accept the orders, you need to ensure that the courier, considering all of its orders, it will be able to find the route among the orders assigned to the courier so that every order in this batch will be delivered on time. So you need also a lot of potential like continuous variables, additional binary variables to ensure this route existence, feasible route existence condition. But we can do it. I'm not against it, I'm a person. But I will tell you what goes wrong, what will be the challenge if you do that in the ADP algorithm. Okay, so then the next piece of our MDP model is this exogenous information, the new orders that join into the system from stage T to T-1 to T. And then we are looking for in the MDP model this policy pi among the feasible policies, which will basically tell you, given the state of your system, what you should do. That's what we are after. And among the feasible policies pi's, we are looking one that will maximize the total reward across our periods. And there's uncertainty in these W's, so you maximize the expected yield. Okay. This is the problem we are hoping to solve. How can you solve it? First thing that might come to your mind is the optimal solution method. Basically, you can write a recursive version of this model, the nested dynamic version, where you will introduce these. This is the critical object. In the talk, rest of the talk, we will hear this quite a lot. The value function, or expected value functions if you want. So what is this value function T given the current state of the system? What I should do now among my feasible actions to get the immediate reward plus for the whole future. What is the expected benefit I would get? So these value functions, they tell you at that point, going forward to the end of the horizon, what is the maximum benefit you would get? Okay, so if you have these equations, these are recursive, you can hope to solve them, right? Okay, value functions. So how you can solve them? This is a recursive system. You can try to do backward dynamic programming. But this will explode, right? If you would like to compute these value functions exactly via backward DP, the state space, action space, like it will all be a problem for you. So it's not gonna work. So you can consider then approximating these value functions to guide you to make good enough decisions, right? So in that sense, what you can do is in these Bellman equations, instead of using the exact value function V, you can put an approximation V bar of it. But then you will approximate these things, but still, this will be, I will say, practically not a good approach because there are still these main challenges that we are still here having a high dimensional integral, potentially for the expectation, plus our decision vectors. Remember this set A. If you want to, for instance, work with a MIP formulation, this is also going to be a complicated model to solve. Okay, so in traditional ADP literature, this is something that is introduced. You introduce this post-decision state concept. And it will help us to break the curse of dimensionalities in this problem. So what is a post-decision state? So post-decision state, while you were going from ST to ST plus 1 in this transition, you put something in between. You break this transition into two. You say, I have, first of all, if I'm in this current state ST, the decisions I decided to take, AT, let me see what happens here. And after you make the decisions and update your state by implementing these decisions, then you will observe the uncertainty realization and update your state once more. So before our updates were for considering both of the A and W at the same time, now you do it sequential. And the state that you find yourself in between, this is what we call the post-decision state. So in our application, actually, if you think about it, what do we have? So this is a state where the couriers are, what they are doing, how busy they are, what are the orders we have in the system. So now our decisions are accept, reject some orders and assign them to couriers or their queues. Do that. And the new state, new orders now, they stay in the system, the ones that are accepted, the ones that are rejected, they are gone. And for the couriers then, whatever extra orders you gave them, this state is updated, right? That's my post-decision state. But then, before I go to the final next stage state, I will observe new orders coming into the system. Okay, so what's the benefit of introducing this post-decision state? So remember this Bellman equation thing that I need to solve here with the approximation. So now what I can do here is, I can break down that expected value type of optimization problem into two by introducing these so-called post-state value functions. So I did nothing new. I wrote exactly the same thing on the previous slide. Only thing is, I have now the S post here, and expectation is moved to the second equation. I did nothing but divided the one equation into two. Nothing is changed. But the beauty about this introduction of the post-decision state and breaking the Bellman equation into two like that is, look at the first equation. There is no expected value. So this became a deterministic optimization problem to be solved if you know exactly what functions you are working with here. And the second one is, there is no decision to be made. This is just a computation of expectation that you can do by means of simulation. So this broke down this difficulty as just you need to work with deterministic optimization models. And the key idea will be now, instead of the original value functions parameterized by state, approximate the value functions parameterized by the post-decision state. Okay. How can you do that? How can you get some approximations of this guy? So pretty much what you can do is, there are various options in the literature. You can build some lookup tables to learn. You can do basis functions. But the one that has been observed to work particularly well for our type of resource allocation problems like right pooling or our type of model is this approach called dual heuristic, which comes from control theory. Because why this is developed, basically the key intuition was behind this is the following. You are trying to learn the value function, but they think the derivative of the value function, like if you give a different input to it, how much it will improve or it will get worse, that is more important in learning these value functions. That's the idea. So let me quickly review. So this is the function that I'm hoping to approximate, right? The post-decision value version. So first thing you can do is, I have these couriers in my system. Let me get one approximation per courier. So I don't want to do this for everybody, for the full courier vector altogether, but I will basically write a separable version over the couriers. This is an approximation. But then you do something more. They usually in the literature, they use a linear form. So whatever the courier state is, you just put a coefficient, and the key of the algorithm, ADP algorithm, will be learning these coefficients. This is like linear regression, right? That's your approximation. Okay, so what is this coefficient? Meaning-wise, in words, it is representing the following. If you give me one more courier of this type, of this state, what is the value I expect from this courier moving forward? So these are these marginal values exactly. And then in the ADP algorithm, it's an iterative algorithm. It is trying to learn these coefficients by basically doing iteration by iteration. What is your current value for this coefficient? What is the new value I got at iteration? And take a convex combination. But what is the new value to get these convex combinations on is, where is it coming from? It's actually using duality. So remember this MIP formulation of my decisions, right? I told you that I can build a MIP model to represent all of my decisions in a stage. And the objective now immediately work plus I put this specific value function approximation there that this method uses. So the idea is this new estimate, the coefficient, the marginal value should correspond to the dual of this model. But we have a MIP. What is the dual? So that's why what they do is instead of using MIP, they relax it, they use an LP relaxation here, and whatever the Fourier type of constraints you have, the coefficients of these, actually the dual variables of these constraints, they are exactly these parameters that you operate with. Okay. But if you would like to apply this traditional ADP approach on our problem, then it's not gonna be, you don't expect it to work well at all because we have very, very complex decisions. First, I don't want to relax this will be too weak. Two, it will nevertheless be difficult to solve, plus these duals will not be that informative. So it's not appropriate for us. Okay, so I will skip these details. So what we identified is, this is more recent from the more recent literature, this neural network based value function approximations could work very well for us because we have much more complex decisions to be made. Okay, let me briefly explain this method. So this NeurADP version of the ADP, it is introduced to the literature by Shah et al. In 2020, and the idea for them was to combine the traditional ADP that I just explained with some deep reinforcement learning ideas to enhance the performance. And this is introduced for a specific right pooling problem, but in this problem as well, you have this one-to-many matching, so which really helps also for our case. Okay. Previously, traditional ADP was using this specific type of value function approximation, linear approximation that I showed you. NeurADP, on the other hand, it is using a neural network as a value function approximation. So you learn your value function approximation in the form of a neural network. So neural network will tell you, give me the state, here's the value function estimate. Okay. So because it's a neural network, it's going to be a nonlinear approximation. It can compactly represent much more difficult decision spaces in a very low dimension. But the key is, okay, let's say I have a neural network to represent my value function, but how can I incorporate it into my decision making now? Okay, so I would like to use a MIP or something to solve in real time to make my actions, but how can I incorporate this neural network into my decision making problem? And NeurADP, in that sense, this paper proposes a very nice two-step decomposition framework to do this. So this is interesting. So what they do is, if I go back here for a second, so if you were to solve this guy, or the MIP version, you have my decisions here, accept, reject, assign to the couriers as the batches, and find the routes of the couriers. So you have everything here. So now NeurADP will break this into two. Okay, it will not decide on all of these things. For one, it will enumerate some possible decisions for some subset, and then it will solve a much simpler MIP than this one. So here we go. So what it does is, it will first of all give a state, right? You have couriers, whatever the states of theirs are, orders came in. You first would like to, for each courier, enumerate, literally, sit down, write a for loop, and enumerate feasible actions per courier. For instance, in this step, say 5 orders came in. Out of this 5, which subsets you can assign to this particular courier, right? If this is available, maybe you can assign, because this courier has a capacity of 2, only 5 choose 2 options you have. You also enumerate all of those and then say, if I assign these 2 to this courier, is there a feasible route to drop all of these things in time? If so, yes, it's a feasible possible action for this courier. So you enumerate feasible actions per courier. And now that you have couriers, their potential feasible actions, just to solve a simple matching problem. Okay, and then we are going to bring it to our actual decision-making problem. And they also incorporate, I will skip the details there, but some deep neural reinforcement learning ideas to do the updates in a much more efficient and useful way. So here's the main algorithmic framework. So we are in a particular stage T, and then we have some orders, and these are, let's say, our 2 courier state. These 2 orders showed up to the system. Shall we accept them? And if so, how to assign them to our couriers? So then the first step of the 2-step decomposition of NeurADP is you enumerate possible actions for each individual courier. So I have 2 orders, 2 bags that came into the system. I have all possible combinations here. Assign nothing, no batch. Assign one of these orders. Assign both of these orders to one courier. You have 4 options. And for each, let's say they are all feasible in this example, say, so I have all the possibilities for them. And then here comes our neural network. So let's say at this stage, we have a currently trained neural network. So you are going to give each courier and each feasible action combination. A courier, a feasible action. If I assign this feasible action to this courier, what is the value I expect? Neural network will tell you. So for each courier, to each feasible action combination, neural network will give you a score. And then you will take the scores, put them into your assignment arcs. If I assign this courier to this action, neural network told me I expect 2.2. You put the scores here, and then you solve a simple matching integer programming model here and implement those actions. And then here comes the neural network-based ML part of the work, is that you have to use this gradient descent-based updates to your neural network so that it's going to learn better from your experiences.
Whether you decide to accept or not accept the order?
Depending upon this IP. So this IP tells you assign nothing, assign both. So if you solve this and both of them say chose the nothing action, you didn't accept any one of those. But if the blue chose this one, this chose nothing, you accepted the blue back, rejected the purple back.
Okay.
Yeah. This is the whole framework. So because I introduced all the greedy details of the traditional ADP, let me also review it for the NeurADP, exactly what type of value function approximation it does and what type of a decision-making IPs it solves. Here's the difference. So now given a state, I am not going to solve the previous myth that I showed you, which will make all of these decisions, accept, reject, assign to couriers, route to couriers. No, we will have this two-step decomposition. First, for each courier, we will enumerate feasible action options, and we will create this matching IP, which will be much simpler than before. So my feasible actions that I enumerated for my courier C at stage T is denoted by the set FTC. So super simple matching IP. What I'm trying to do for each courier at that stage of the system, among these feasible actions, these are binary variables, pick one. So ATC F is one if at stage T for courier C, among the feasible actions set this F action, if you selected it and assigned it to this courier or not. So for each courier, pick an action. It will be do nothing, or here's your new set of orders. And then for each order in your system, you look at which couriers you can assign. Among the ones that is whose eligible basically feasible action includes this order. So in other words, left-hand side is whether you assign this order, how many couriers you assign this particular order of, it can be assigned to at most one courier, right? And then the objective, which is the interesting part. Among all courier and feasible action matchings, you first of all get the immediate reward, which is how many orders they are going to deliver with this decision, with this particular assignment. But for future, what do you expect? Neural network tells you what you expect from the future. Neural network tells you, if I assign this courier F, this courier C, this F action now, in the future, I expect from this courier this score. So thanks to this two-step decomposition, you simplify the MIP to be solved in real time for decision making. And neural network, although it is a highly nonlinear value function approximation, it only comes as constants into this MIP. That is, I think, pretty cool. Okay, so I will skip the details, and I already actually give the algorithm. Maybe for the sake of time, I will just show you the main findings of our experiments. We have experimented quite a bit with different networks, different geographical areas, different configurations for how many couriers, how much of delays you accept, whatnot. And we compared against these two main classes of policies. In each we have multiple policies, but first class is myopic, you ignore the future. Second one is deep reinforcement learning based algorithms inspired by the literature. So this one, which is coming from, again, inspiration from the literature, this network, neural network for this one, only tells you accept, reject decisions, and your assignment is based on a predetermined heuristic, rule-based heuristic. And again, for the sake of time, maybe I'll skip the details, but we also have some non-trivial ways of generating what is the maximum number of orders we can fulfill. It's not the number of orders that arrive. If you just work with number of orders that showed up in the system, it is too big of a bound. We want to get something that is more feasible, achievable, so that we can assess the quality of our solutions better. Okay, so here are the comparisons. Among the orders, what percentage our NeurADP policy can serve, it is almost close to, in this base case example, broken example, it's about 98% of the orders NeurADP can fulfill, whereas the DRL and myopic ones are at most reaching up to 91% of the orders that showed up, but not the orders that showed up based on our non-trivial upper bound. So in other words, what's happening is we are getting strictly outperforming policy results. And this is interesting. Myopic is actually doing better than DRL because DRL is only making accept reject decisions, but myopic, although it ignores the feature, it is still trying to make all the decisions for the chemistry. And then we also have some other more detailed analysis, what's going on with this policy, especially what's the value of this optimization in this operational setting. We see that the most benefit we get is, first of all, when you have fewer couriers that are working at near their capacities, so you don't have like large capacities, and you have much tighter delivery schedules, then this optimization with NeurADP can save you much more. But it is actually much more important that we observe is like one intuitive policy would be if you have couriers with certain capacities, give them as many as possible and then ship them, right? But no, our policies showcase that actually it is a better way of if you give them strategic number of orders, somehow they can come back to the depot quickly. You don't want to give them just one order, but there's this sweet spot that you also want them to come back quickly to help you with the upcoming orders. Okay, so this is the summary. We look at this ultra-fast delivery problem, especially focusing on the order dispatching and matching aspects. We introduce compared to literature some new features to make it a bit more realistic, a bit more complicated, and we find NeurADP as a very suitable approach, and our experiments confirm that it actually has been the case. We outperformed all the benchmarks that we currently tried. If you're interested, just yesterday or so, we finished the paper for you, so we posted online. You can find more details there. Okay, thank you so very much for your attention.
Questions here.
What are the solution times for your algorithm?
So what are them exactly? So we didn't put too much restriction on the training because there is this learning phase, right? We are learning the NeurADP algorithm, and the key here is like we are okay to spend hours or if not a day to learn, as long as like you don't think your demand patterns, for instance, they don't change significantly. Once in a while, you may want to retrain. So I don't recall exactly how many hours or so we were spending for the training. It was not bad. It's not like a day or so we run these things. It's in a matter of hours. But then the important thing is in real life, how fast it is, right? So, and because we are solving a super simple IP, because also the couriers have capacities, let's say few, which drops this feasible options quite a bit. So the solving the matching IP is pretty fast. It's ignorable part. But yeah, in the paper, I hope you reported the exact training times.
No, I was more interested in the real-time solution.
Real-time solution is super fast. Once you have the neural network trained and fixed, it's just a matter of solving that IP. And here, as I said, sorry, just this one. So how many couriers and how many orders you have in the system? But the important thing is these sets Fs, because of the strict delivery deadlines and because of the courier capacities, this is actually something that we can fully enumerate. This is a very small number of options you have for each courier at any time. In the original NeurADP paper, for instance, for right pooling, their system doesn't allow you to enumerate them all. They were just heuristically enumerating a small subset of it. But for our problem, we can enumerate all of these guys. And despite that, this matching IP is super fast. We didn't even need to employ special matching algorithm here, just solve it as an IP. I mean, all that it takes in the training, you solve so many of them. I think it takes, if I recall correctly, like a significant portion, like 30–40% of the overall training time still, because we do it so many times. But then real time solving one of them, so simple.
Matthias has a question?
Yes, thank you, Margarita. Can you hear me?
Yes.
Great. So thank you, Merve. This is a nice research. I was wondering, this is like an advanced value function approximation scheme for this problem, and it looks quite good. But I was wondering if you tested something simpler, like a parametric estimate of the value function. For example, a linear estimate of the value function trained via recursive least squares or something more standard. I wonder what's the added value over like simpler VFA approaches.
Indeed, Matthias, that's a great question. I'm sure like referees will also ask us the same thing. To be honest, we haven't tested any traditional ADP type, like traditional approximations, because we still believe that like if you don't have this decomposition, solving these MIPS will still be, I think, challenging. But also we thought that linear approximations will not be good, inspired by again what happens in the right-handed literature. So
I'm not like thinking about like a dual like linear approximation like ALP stuff. No, that doesn't work good. I agree with you. But working with a value function approximation that is linear in some features and calibrate these parameters via regression under simulation.
Right.
That kind of stuff. And you can use that linear function afterwards in the matching IP.
Yeah, so I would expect very inferior things, because I think these value functions, if you simulate a little bit then, or even like you do for smaller examples, some optimal policies abandon way, like you get the value functions, they are highly nonlinear. So I would guess linear version wouldn't be good, but I think it's a very good idea to test it nevertheless, right? Because if the simplistic thing you can try, if you cannot beat that, of course, like there's no more point. But to be honest, we haven't tested anything simple like that. We were mostly targeting maybe we should test traditional ADP, but after identifying all these potential drawbacks, we decided that there's no need. But just for fun, I think we should do it.
Thank you. I'll send you an email with some related papers.
Awesome.
Thank you very much for your presentation.
Of course, thank you so much for being here. Any other questions? Yes.
Professor, are you considering that the autocorrelation between order are seen? Because you say that that's are stochastic, but could be they have some correlation between them and could be
The orders, right?
Yes, the orders.
Yes, indeed. So how we model the stochasticity, we indeed look at the daily profiles, for instance, or some other features, geographical reasons. So indeed. Because in reality, like you have certain surges during the day to make more orders. Indeed, we use that type of stochastic model to generate these orders. Yeah, we consider correlation in generating the orders. But the good thing about this ADP type of methodologies, it is mostly simulation based. You learn by just simulating options from the distribution. You don't need to, although you have such a complicated stochastic model for the order distribution, it doesn't matter because it doesn't come into the model, right? You just need to be able to sample from it. But we do consider correlations for sure for the time of the day or some geographical location-based features, we indeed consider it.
I also have a question because you mentioned at the beginning that you have some upper bounds too, like and I was wondering, like these upper bounds is like assuming perfect information or something.
One is indeed like that. So one is this one. So we have the training phase, and then how we evaluate is we have say 20 days or so we test, right? So one is we are cheating exactly, we are doing the perfect information. For each day, we are specifically just for day. Every sample comes from that same day, same sample over and over again. We train a NeurADP, basically a policy for that day, assuming that we know exactly what's going to happen to that day. So that's exactly the perfect information. The second one is a different kind of a relaxation. This one, we just relax basically the travel times. We assume whenever you batch somebody, they are right back at the depot. It takes zero time for them to deliver the orders. But we still have all the stochastics and everything else. So this is a different kind of relaxation, and we pick best of the two.
And also, you also said that you consider basically like the routing part, because sometimes you can have like multiple, like a courier have like multiple orders. So how is that incorporated in this approach?
Great question too. So that's the beauty, I will say, of again this two-step decomposition of the NeurADP, especially if you were to do MIP, you need to model it.
Yeah.
But for this one, it's all in here. While I'm enumerating these, like I have this, let's say, fully available.
You're like.
If I
people
assign these
system.
three,
Yeah.
first, I can easily find solve a specific thing, or even by enumeration of the sequence options, right? These are small sizes. You find what is the best route. So we find the one that has the minimum total travel time. And actually, right before in the policy, while we are implementing, we dispatch somebody, we give them the tour with the smallest completion time. So everything goes into this, which is just the enumeration.
Okay. Is there any slack for the delivery? I mean, like 10 minutes, or can it be 10.5 minutes or something like that? Because being a little bit, I'm thinking about real
Travel times, right?
Yeah,
For instance. Yeah, we do not consider travel time uncertainty, nor like the time uncertainty making the deliveries.
Yeah.
That's something else to incorporate outside. But the travel time uncertainty especially will make it much more complicated. But we are assuming that since these are, again, my motivation at least is these are super ultra fast delivery setting, right? So let's say right now, if you are gonna dispatch somebody, you know the traffic conditions. Exactly, right? To ensure feasibility that this guy can drop all of them on time. And if you're talking about 10 minutes or so, traffic conditions, whatnot, weather is not going to change drastically. So you can get accurate enough deterministic time estimates, I would say, to put them. You know, so that's the idea. Again, this ultra fast thing comes into play, that it is not as important as the uncertainty in the orders, I would say.
Any other questions?
So maybe one thing I would say, if we have any master students here, we are actually inviting applications. If anyone is interested in doing a PhD in the UK, so the deadline is late January, but we also accept actually consideration of the applications after the deadline. So if you are interested, and also by the way, I also learned this trip that actually our universities have also an agreement. Yes. So if you are going to do a PhD, for instance, a couple years here, a couple years there, we can also collaborate. So if you're interested in optimization under uncertainty, for instance, I will be happy to talk to you now or in the future. So you have allies there. So whenever you're interested, if you know anyone interested,
a good offer,
just let us
4
know.
years full funding.
Yes, funding comes directly, government, university, they ensure that. And additional funding, I don't know exactly how it works, but at least you have full guaranteed funding for this. Okay, thank you.
Okay. Okay, so thank you all for coming. That will be it for the seminar.
Thank you so very much, everyone.
Very much.